Okay, so we're gonna pick up where we stopped in class today. So I want you to kind of refresh your memory. We're gonna go over a couple problems, and then the practice that you had behind this is something that you want to do. Try them. There is a QR code at the end of the practice to determine whether you got the answers correct or not. And as always, I will post my key once it's complete. Okay, so the question says a 13-foot ladder is leaning against a wall. Suppose that the base of the ladder slides away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? So we don't really have known variables. It's a little hard to tell what variables to use. The previous example, we're talking about radius. So it's R for radius, A for area. Those are common, but this one maybe not so much. So one of the things I want to do first is to just draw a picture and put some variables on the picture so that we get an idea of what it is we're talking about. So we have a wall on the ground, and then there's this ladder that's leaning against the wall. Please ignore my crooked ladder. Do not climb this ladder. This is a dangerous ladder. Okay, so we have some things. We're dealing with a right triangle. The minute I see a right triangle in my picture, the first thing I'm going to do is kind of label my sides A, B, C, because we're used to using those variables for a right triangle, Pythagorean theorem, and things of such. So I'm going to put some variables on my problem. That's important because when we start defining rates of change, we need those variables to know what we're talking about. So the first, I'm going to go back and read again. It says a 13-foot ladder is leaning against the wall. So I know right now that this C is 13 feet. Okay, so again, the givens, I know my C is 13 feet. So I'm going to write that on my page. Okay, suppose that the base of the ladder slides away from the wall. So the base of the ladder is moving that way, which means my B is increasing. The distance between my ladder and my wall is increasing. So that's a positive rate. So dB, because the length of our base is changing with respect to T, is a positive 3 feet per second. So I know that. Here comes the question. So what I'm trying to find. It wants to know how fast is the top of the ladder sliding down the wall. So now we're talking about A. If we pull out the ladder, the top is going to come down. So what we're looking for is dA dt. I want to know what that is. Now, because we know B is increasing, if we think of the situation, A, when that ladder comes down, is going to decrease, which means my dA dt is going to be negative in this problem. So knowing that up front can kind of lead you to see if you got the right answer or not at the end. Okay. It says, how fast is the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? So when B equals 5 feet. That's another thing we know. So B is equal to 5. I'm not going to put that on my picture. So now I need my equation to figure out the relationship between the 3 sides of my right triangle. Well, that's an easy one. We've kind of seen this problem before in geometry. We're just taking it to a new level. So a squared plus b squared equals c squared. Good old Pythagorean theorem. He's one of the most useful formulas we have in mathematics. So thank you, Pythagoras. Okay, so now it's all about figuring out what the derivative is, because that's what we're looking for. So I'm just going to derive my Pythagorean theorem. So I'm going to get 2a, and we're taking this with respect to time. Okay, remember our units here, that seconds tells us we're taking the derivative with respect to time. Okay, so I'm going to undo that. So dA dt, because of our nice implicit differentiation and our chain rule there, plus derivative of b squared is 2b dB dt, good old implicit differentiation, equals 2c dc dt. Okay, so we got our derivative. So now it's about time to start plugging in. So I'm going to plug in everything we know from that top line, that given line, and then we're going to solve for the thing that we're looking for. So let's start plugging in. 2. I don't know what A is, But if we go back to our triangle and we think about the Pythagorean theorem, we can actually solve for A because we know B, we know C. So we're going to use Pythagorean theorem again to solve for A. So A squared plus 5 squared equals our 13 squared. So if we solve, we get A squared, 169 minus 25, which is 144. So that means our A is 12. So now I can go back and plug it in. It's 12 and it's feet. So we're going to use that. Our dA dt, that's what we're solving for. So he's going to stay in our problem. He's the variable. Plus 2, my B value was 5 from the top or from my triangle. My dB dt was a positive. Sorry, let me get the units on there. Don't leave off the units are important. So 5 feet, and then our dB dt was 3 feet per second. Equals to our C was 13. And then we don't have a dC dt, but C was in fact the ladder from the problem. So C is not changing. That's important. So if it's not changing, that means its rate of change, the dC dt, would have to be equal to 0. So 0 in there. Okay, if it's not changing, the rate of change is 0. I mean, it makes sense. But usually when you're doing a problem and you're missing something like that, it's usually because we have to go back and solve for it, like we did the A, or if we have a rate that we don't know, there's a big possibility that that rate is 0. So we always want to go back and check to see, to make sure that something is changing. Okay, so I'm going to kind of simplify this out. We get 24 feet here, dA dt, plus, we got 2 times 5, which is 10. 10 plus 3 is 30, or 10 times 3 is 30. And we get feet squared per second. And then this is going to be equal to 0. We're solving for dA dt, so we have 24 feet dA dt equals a negative 30 feet squared per second. And we knew that was going to happen. We kind of predicted it from the beginning to see that. So I'm going to actually go on to another screen. So I want to actually get this, see if I can connect, not that. Never mind, forget about what I said. Okay, and then the last step for us to do is to divide by 24 feet, or multiply both sides by 1 over 24 feet. So 1 over 24 feet. Remember, division is just the multiplication of the reciprocal. So that's going to cancel out. And over here, I know you probably still have some room on your paper. Our dA dt, which is what we're looking for, negative 30 over positive 24 is going to give us a negative 5 over 4. And then our feet here are going to cancel out one of our feet from the top. So we get back to feet over seconds. If we get decimal form, that's negative 1.25 feet per second. We predicted it to be negative. The math shows it's negative. And so that's really the process there. So this one's not too bad, Pythagorean theorem. This is kind of a common question. If any of you guys recognize the shirt I was wearing today, it's geared towards a problem like this. Okay, so let's look at the last one. The last one's also a common problem. It's actually a pretty easy math problem. The setup is the thing that's the hardest part about this problem. So it says a man 6 feet tall walks at a rate of 1 foot per second toward a light pole 16 feet tall. When the man is 10 feet from the base of the light, what rate is the length of his shadow changing? So let's get a picture. So here we have the ground, and don't make fun of my picture, I'm not an artist. Here's the light, kind of like Here's some light coming out from the light pole. Again, don't make fun of me. Here's a man. He's walking towards, maybe he's looking at his phone, as teenagers often do. And the light comes down, hits the man, and creates a shadow right here. Okay. So we know that the man, let's put M for the man, and let's use X for the light pole. I don't know, I'm just choosing variables. It really doesn't matter what you choose as long as you know what it represents. So I'm going to put some givens. So we know that our men, so M equals 6. He walks a rate of 1 foot per second towards the light pole. So that means that this distance between him and him is changing. So I'm going to put that A. So we know now that dA dt is equal to -1 foot per second, because he is walking towards the pole, which means A is decreasing. Okay, and then the light pole itself, the X, is 16 feet. And I forgot the units here, but that's in feet as well. Okay. It says when the man is 10 feet from the base. So when A is 10, that's another thing we know, 10 feet. From the base of the light, what rate is the length of his shadow changing? So we're looking the area between here, let me get a different color. We're looking at the length between here and here. So we don't have anything that's labeled as that, so I'm going to put this as B. Okay, so then we want to know, so our find is really how the shadow is changing, and the shadow is being measured by B. So now it's time to get an equation, and this is what makes this problem a little bit difficult for most students, is what kind of equation would we even use for this? Okay. If we go back to geometry, one of the things that we learned in geometry is about similar triangles and how the proportion of the sides are equal when it comes to similar triangles. So we're going to actually use a proportion to solve this. So if we take the length or the height of our big lampposts, that's going to be equally proportioned to the height of the men. Okay. And of course, the base of the entire distance of the bigger triangle is actually our A plus B. And then of course, the base of the smaller triangle is just B. Now, that's a lot of variables to deal with, and I don't want to deal with all those variables. I know some things that are not changing, and it's good to plug in the things that are not changing before you start deriving, because it kind of helps in your derivative process. It can make a derivative easier. So I know, like x is equal to 16. That's not changing. Okay, it's constant, so let's plug it in before we even start our process. The height of the man is also not changing in this moment, maybe over a big length of time, but not in the moment. But B is changing. So this kind of eliminates some of the variables we use. Now we can take the derivative as is, and that would mean that we would be using our quotient rule, or we can simplify this equation up front by just doing some cross multiplication or multiplication by the denominators. So 16 times B, so cross multiplying here, equals 6 times that entire length. Now if I do some more distribution, I get that. Now those B's and that 6 look very similar, so I'm going to make those capital B's, if you guys don't mind, so that we can distinguish the difference between our 6 and our B's. So my red and my black are going to be mixed here, but that's okay. Okay. just so that we can distinguish between the 6 and the b. That would make it a little bit easier. Now, again, I can derive, or I can keep simplifying by subtracting that 6b onto the other side to get 10b. And once I do all of that simplification, the derivative of what's left is pretty easy because it's really just a coefficient, and the derivative of b gives us db dt equals to 6, and then the derivative of a gives us dA dt. That's a pretty easy derivative to take. So now it's just about plugging everything in. So I don't know what dB dt is. That's what I'm trying to figure out. But I do know what dA dt is, so I'm going to plug that in. And that's going to give me -1. Okay. So I'm coming up here so I don't run out of room. So our dB dt is equal to -6 over 10. Now I didn't use units and I apologize for that, but let's talk about what b is. B represents the length of the shadow, which means my length is to the first degree. My length is measured in feet, not equals. I don't know what I'm doing. Ignore that for a minute. Is equal to -6 feet, because our length is measured in feet. Again, ignore that. That looks like 2 F's. That's better. Feet, and then our time was measured in seconds. Okay. If we want to simplify that, I believe -6 over 10 gives us -0.6 feet per second. Okay, so go ahead and finish out those notes. Try some of the problems that are on the next page. Look at the QR code at the end. There are 2 on there that are pretty difficult, but 3 of them are actually not too bad. So try the ones. I'm going to post the key to both this and the practice, and that way you can check yourself. But you can always just check the answers by using that QR code. Okay, if you have any questions, come and see me Monday.